Hello everyone, the power of pi here, and today we're going to be looking at the 2020 AMC 12B problem 24. And I believe this was also problem 25 of the AMC 10B. So let Dn be the number of ways of writing the positive integer n as a product of these fi's that are strictly greater than 1. And then the order of which we list matter, and then they give us an example. So 6 can be written as 6. 2 times 3, 3 times 2. So D6 is equal to 3. And our goal is to find D96. So D96. So maybe the first thing we can do is prime factorize. 96 is 32 times 3, which is 2 to the 5th times 3. So what I'll do is I'll write it as its product of repeated prime factors. So we have 5 2's and 1 3. So evidently what we see is that k must be less than or equal to 6. If k were bigger than 6, that would force an fi to be 1, which we cannot have according to the problem statement, since it must be strictly greater than 1. So with this equipped, let's just proceed with casework. So k equals 1. So again, if it's the product of only one integer, that'll be 96. So there's one way to do that. K equals 2 is also pretty easy to take care of. What we can note is that these fi's must be in some order, some 2 to the power of a, and then some 2 to the power of b times 3. The 3 must belong to one of the fi's. So with this, we know that a plus b with a plus b equal to 5. So we can now do casework. Suppose that b were not 0. Suppose b is a positive integer, and a plus b was 5. There is by stars and bars, or simply by listing 4, 1, 3, 2, 2, 3, 1, 4. There's 4 choose 1 ways to select this. Now, if b were to be equal to 0, then that forces a to be 5. So there's only one way to do that. And then there are 2 ways to arrange our 2 to the a and 2 to the b times 3. So that's 2 times 4 choose 1 plus 1. So 10 ways in this case. So let's move on to k equals 3. So maybe a similar thing, we call them 2 to the power of a, 2 to the power of b, 2 to the power of c times 3. So now what I'm going to do is I'm going to actually share what I did that was actually wrong. So I kind of proceeded with the same logic. First of all, if c is not equal to 0, c is positive, then a plus b plus c is 5. By stars and bars, this will have 4 choose 2 solutions. If c were equal to 0, then that reduces to a plus b equaling 5. And there's 4 choose 1 solutions. If you add this, you can just, of course, add it, but that's a nice application of hockey stick as well. We know that this is 5 choose 3, which is 10. So there's 10 such pairs up to this, and then we can reorder in 3 factorial ways. But of course, this would overcount when a equals b. If a were to be equal to b, we have 2 of the same identical object and 1 different. So there's only 3 ways to arrange that and not 6. So how many ways can we have a equal b? That can be when a equals b equals 1 and a equals b equals 2. So 2 ways to do that. And then we've counted them 6 times when we really want to count them 3 times. So we need to subtract them off 3 times. So this evaluates to 54, but this is actually a wrong conclusion, and I'll explain why. So k equals 3. So say, for example, we chose a equals 1, b equals 3, and then that for c equals 1. But then say we were to also choose, and then I'll probably write out what this is. This is 2, 8, and 6. But then say we were to choose that a equals 3, b equals 1, and then c is uniquely determined to be 1. This would be 8, 2, 6. As we can see, they're the actually exact same thing. 2, 8, 6, 8, 2, 6. We can reorder them and they'll be the same thing. So really what we actually need is we need something such as a greater than or equal to b, so that we don't overcount pairs. So let's go ahead and do that. So again, it's 2 to the power of a, 2 to the power of b, 2 to the power of c times 3. Let's proceed with our usual casework. Suppose that c were not equal to 0. Then we have a plus b plus c equals 5. Now there's 4 choose 2 ways to normally do this. Let's first count the number of ways where a is strictly greater than b. If a were to be equal to b, we can have a equals b equals 1, a equals b equals 2 for 2 possibilities. And then of these, exactly half of them have a greater than b, with the other half having b greater than a. So this is 4 choose 2 minus 2 over 2, which is 2. So for 2, we have some a greater than b, and then a uniquely determined c, which we know are all different. So we can multiply by 3 factorial. What about if a were to be equal to b? Then we have two possibilities, a equals b equals 1, a equals b equals 2, with c being uniquely determined. And then we have 3 ways to kind of shuffle them around. So, and then case 2, kind of subcase 2 is when c equals 0. If c equals 0, then a plus b is 5. So 4 choose 1 ways to select a and b, but a cannot be equal to b, obviously. So exactly half of them satisfy a greater than b. So with c equals 0, a plus b equals 5, we see that these 3 numbers are distinct, so we can multiply by 3 factorial for rearrangements. So if we were to add 2 times 3 factorial, this thing, plus 2 times 3, plus 2 times 3 factorial, these 3 things, we get 12 plus 12, 24 plus 6, 30. So 30 in this case, let's see, that was a wrong approach. 10 in that case, 1 in that case. And then now we get into kind of the straightforward territory. So now let's cover k equals 4. Again, 2a, 2b, 2c, 2d times 3. Now it's probably more straightforward to just list our possibilities. We can't have a equal 4 or greater because b, c, or d must be at b and c must be at least 1. So if a were to be greater than or equal to 4, a plus b plus c is greater than or equal to 6. So a can be a max 3, and then 2 to the power 1, 2 to the power 1, 2 to the power 0 times 3. Or we can have 2 squared. In that case, 2 squared, 2, 1, 2, 0 times 3. Or what we could have is maybe 2 squared, 2, 1, 2, 1, 2, 0 times 3. Or we could have finally 2, 1, 2, 1, 2, 1, and then 2 squared times 3. 3, 4, 4, 5. Wait, hold on. Okay, yeah, this is 2 to the power 1. All right. So now how many ways are there to rearrange this? This one, we have 2 of the same object and 2 different. That's 4 factorial over 2 factorial, 12 ways there. And then similar things for this kind of thing, 12 here, 2, 1, 2, 1, that's 12. And then here we have 3 of the same, 1 and different. There's 4 ways to do that. If you add these up, you get 40. And then let's tackle k equals 5. For this one, I'll just list 2, 2, 2, 2, 2, 3. These were all the prime factors with repetition. So to get k equals 5, we either combine a 3 and a 2, or we combine a 2 and a 2. If we combine a 2 and a 2, we get 4, 2, 2, 2, 3. And if we combine a 3 and a 2, we get 2, 2, 2, 2, 6. So this has how many ways to rearrange? 5 factorial over 3 factorial, which is 20. And then this one has 5 factorial over 4 factorial, which is 5 ways. So there's 25 ways for that. And finally, k equals 6. Then we're just rearranging this. So 5 2s and 1 3s, that's 6 choose 5 or 6 ways. And then now we're ready to add. So 6 plus 25 plus 40. And then I'll just refresh you guys on our other cases. We had 30 here, 10 and 1. So 30 plus 10 plus 1. So if we add this, we get 31, 71, 101 plus 11, which is 112. And then if you go back, that was A, and we are done. So hopefully you guys enjoyed that, more complicated example. Again, this was my solution. There's probably better ways. Make sure to like, subscribe, and I'll see you guys in the next video.